So I usually start class with a hanging magnet, and what you'll notice is that the magnet points in a certain direction, and if I spin the magnet so it's pointing in the opposite direction, it'll turn around and point back in that direction. So the North Pole, or the pole of the magnet that points north, we call that the North Pole because it points north. That's where the name comes from. And it means that magnets have been useful for thousands of years, because when people discovered naturally occurring magnetic material, they found that they could use it to find directions like north. So it was very useful at sea. And so a compass is just a very small floating magnet. So if you put a magnet, like a simple thin bar magnet, on a pin, or you float it on water, or you hang it from a string like we did, so it's free to turn, it will always point in the direction north. So why does it point north? Well, what we discover about magnets is that if we take two of them and find the north pointing pole of each one, then we find out that like poles, just like electric charge, like poles repel and opposite poles will attract. And so the pole that points south will always be attracted to the pole that points north. And so magnets affect other magnets. And I can't show you this now, but they're not affected by electric charge. So what that means is that the Earth is a magnet. And it leads to the odd situation, or at first confusing situation, that since the North Pole of a magnet points toward the North Pole of the Earth, then if the Earth is a magnet, that must be the opposite pole in the north. So we have, and we also, it's useful to notice that the axis of the magnet and the axis of the Earth don't exactly line up. And so this axis is the spin axis, the axis around which the Earth spins, and this axis is the pole axis, the axis that goes through the imaginary bar magnet inside the pole of the Earth. Okay, so the Earth's a magnet. Let's put this away. Magnets attract and repel, as we learned. If you hang a magnet up, it responds to the Earth being a magnet and points north. And so we can use a magnet, a hanging magnet, or a little magnet pivoting on a pin in a compass, to find the direction of north. So anyway, we might be curious what the magnetic field looks like. And so since a compass responds nicely to a magnetic field, we could take a magnet and put a bunch of compass needles all around the magnet, and they would point in the direction of the field. So they would kind of trace out the field lines. So you can see field lines coming out of the North Pole, going around, bending and going. So a compass here, the North Pole is going to point this way. And up here, you see the North Pole is pointing in the opposite direction that the magnet's pointing, because the field line bends around. The shape of this field is familiar to us because it looks like an electric dipole field. An even better way of kind of mapping out or seeing the field of a magnet is to sprinkle iron filings around it. whoops, yeah, let's take this out here. And so maybe you've seen this before. If we take a magnet and we sprinkle iron filings around it, it gives us the shape of the magnetic field. And that's because each little filing becomes magnetized, because iron becomes magnetized. And so all the filings become just like little compass needles, and they point in the direction of the field, and so they trace out the way the field of a magnetic dipole looks. Okay, I paused the video and rearranged things, deleted a few things, and brought in some new figures. What I didn't mention was that we know about a bar magnet, and we also, whoops, familiar with the idea of a horseshoe magnet. So you can imagine here, you just take the bar magnet and you bend it into a horseshoe, and one side is a north pole and the other side is the south pole. And the field lines will leave the north pole and go into the south pole. So if you look at this figure, you can see what the field looks like. So let me put this away. Bring up the thing that shows the magnetic field. We could show this with filings like we did with the other magnet. And so the field lines come out of the north pole and go into the south pole. And what it means is that there's an area here, which will be useful to us when we do some experiments later, where the field is almost uniform. It's pretty strong and it's uniform because you have a north pole here and a south pole here. And so you have a lot of field lines going across, and they're almost straight. So the field in this area right here gives you a pretty strong and uniform magnetic field. That will be useful to us later on. Okay, so that's the bar magnet, that's the horseshoe magnet. And then we talked about the fact that iron filings can act like little magnets. They're little filings of iron and they become magnetized. And this is what we know about how iron becomes magnetic. It turns out that if we take a piece of magnetic material and put it under a microscope, we see these areas, this says 20 micrometers, you may not be able to read it. And so the metal, in this case it's not iron, but it's another kind of magnetic material, organizes itself into these clusters or little areas that are called domains. And each of these domains is magnetic. So if we draw a schematic of that, if we take, say, this figure, well, let's take this one. You can see that if you have a material where the domains are randomly oriented, each domain is itself magnetic, but each of the domain magnetic directions is randomly oriented, this particular piece of iron or magnetic material will not appear to be magnetic. But if we put it in the presence of a strong magnet, then the domains can all line up in the same direction. And so this you can think of as a piece of unmagnetized iron put in the presence of a magnetic field becomes highly magnetized. And I have another figure to show you that illustrates that. So here's a bar magnet or a piece of iron that's not magnetic. If we take that bar and we put it in the presence of another magnet, that magnetic field will make those domains, exert a force on those domains, and tend to make them line up with the field, so that the non-magnetic piece of iron, the iron filing, becomes magnetic. All right, one more thing. That's all about how iron becomes magnetic and the concept of magnetic domains. The next thing is this: we have this very interesting phenomenon that I have a way of demonstrating this in class, but we're not in class. So suppose you take a magnet, a bar magnet. It has a north and south pole. And if we think of this like electric charge, there's a positive charge and a negative charge, and they're separate. But what happens is if I cut this in half or break it in half, the two pieces end up having a north and south pole. And no matter how many times I break it in half again, each piece is still a dipole. So we run into this interesting and surprising result that there are no magnetic monopoles, and that every magnet that we know of is a dipole. It has a north and a south pole. And so how do we understand that? I'm going to pause the video and collect some new figures. Okay, so what we've learned so far is the things about magnetism that have been known for hundreds or even thousands of years. There were certain magnetic materials, they attract and repel each other. Those materials can be used to make compasses that people used in navigation for centuries. But as far as we know, there's no connection. Up until 200 years ago, there was no connection between electricity and magnetism. They were two entirely separate and distinct phenomenon. Electric charge did not have any influence on magnets, and magnets didn't have any influence on electric charge. And electric charge was really not very useful until we learned how to make batteries and were able to have currents and current-carrying devices. Magnets were interesting and useful because they allowed us to navigate around the world. So we arrive in 1820, and we have a person by the name of Hans Christian Ørsted, and he was a Danish scientist. And I'll show you a simplified circuit from his original circuit. Here's a battery and a wire, and we close the switch and we have current, and what we notice, and this is what happened to Ørsted, just accidentally noticed that when there was current in the presence of a magnet, a compass, that the compass needle deflected. So this was a surprise. So let's take a look at Ørsted's apparatus and how he used it. So you'll notice that there were two wires carrying current, and it goes across to the right, coming on the plus side to the minus side, and so there's a current flowing through that wire, and underneath it is a compass needle. So when the current flows through the wire, we see that the compass needle deflects. The compass needle, the current's going through the wire, and the compass needle deflects in the direction you see. If we were to turn the current around, going the other way, then we would see the compass needle deflect in the opposite direction. So this was unexpected and surprising because there was no known connection between electricity and magnetism. If we change the wires and hook them up across the bottom, and we run current across the bottom, then the deflection of the magnetic needle is, again, opposite, in the opposite direction from where it would be when the wires were connected around the top. So let's take a look at a more modern looking version of Ørsted's experiment. There's the wire, there's the compass needle. We put the compass needle close to the wire, and if there's no current in the wire, the needle isn't affected at all. But when charge flows through the wire, the compass needle deflects in the manner that we described earlier. So the conclusion of this is that a wire has a magnetic field associated with it. So naturally what we want to do is we want to figure out what that magnetic field around a wire looks like. Remember, the way we see a field is to use iron filings or a compass needle. So here we have a vertical wire and a plastic platform. We actually have this for lab. There's a battery, sends current downward through the wire, and then there's this horizontal platform that we can sprinkle iron filings or put little compasses. And what they do is they trace out a field which is circular, and that explains what Ørsted saw. The field on one side of the wire is in one direction, the field on the other side of the wire is in the opposite direction, and the field lines are closed circles. They have no beginning and no end. So think about it, no beginning and no end. That's very different from an electric field line, which starts on a positive and ends on a negative. So those closed loops, if we change the current in the other direction, the direction of the field will then circulate in the other direction. And so we want a convenient way of knowing the current, what's the direction of the field, and knowing the field, what's the direction of the current. So for that, we have a rule. We have a way of doing that using the right hand, and we call that right hand rule number 2. And this figure will show you a demonstration of well, first of all, okay, this shows you the closed loop situation that I was just talking about, and it also is a way of understanding since the field lines don't start on the North Pole and end on the South Pole, they just go right through the magnet. So the North Pole isn't a place where the field lines end, it's just the place where the field lines come out of the magnet. And the South Pole isn't, the North Pole isn't where the field lines begin, and the South Pole isn't where the field lines end. It's just where the field lines enter and leave, and they're all closed loops. So anyway, getting back to what I was started on, the right-hand rule, if we take this figure, you can see that if I curl my fingers and point my thumb of my right hand, that will tell me the direction of the current and the direction of the field. So supposing we know the direction of the current, we can predict the direction of the field. Or if we observe the direction of the field, we can predict what direction the current's going in using right-hand rule. And for us, we're going to call this right-hand rule number 2. Some videos use a different numbering system, but just learn our numbering system. This is for a straight wire and a circular field. We use the right hand with the fingers curled, and we call that right-hand rule number 2. You can see that demonstrated in both figures, the direction of the field and the direction of the current. And, if the current were turned around, you would turn your hand around and it would tell you that the field was in the opposite direction. Now, supposing we take the straight wire, let's do something different. Let's take the wire and bend it into a loop. So the wire comes in, the current comes in straight, goes around a loop, and then goes out straight. So there's a straight wire with a loop bent. Yet each section, each little piece, can be thought of as a small piece of straight wire. So let's use right-hand rule number 2 at this section of the wire. And I point my thumb in the direction of the current. My fingers curl around the wire and show me that the field is coming up out of the coil. If I go to this section of the wire, the current's going that way. I point my finger. And so in each section of the wire, using right-hand rule number 2, we get that inside the loop, the current is coming up and out of the loop. So here's a diagram of that showing that if you have a current loop, the field comes out of one end, goes into one end, and comes out of one end. So think about how that is the same as the dipole magnet we just looked at. So we can think of a current loop as a dipole magnet. But in order to get the direction of the field, rather than use the clumsy way of using right-hand rule number 2, we have a new rule called right-hand rule number 3, where you curl your fingers, right? The current now is what goes in the circle, and the field inside the circle is either straight up or down. So curl your fingers in the direction of the current, and your thumb will point in the direction of the field. You could go back to this one and see the same thing. If you run your fingers around the loop, your thumb will point up. So that means the front side, the top side of the coil is the North Pole, and the bottom side is the South Pole. And so you see there's really no poles. There's just one end where the field lines come out, and the other end where the field lines go in, and the end where they come out we call the North Pole, and the end where they go in we call the South Pole. And the field inside the loop is all in one direction and fairly uniform, actually. So that's right-hand rule number 3. And if we take many loops, so that we have actually a coil of wire, then once again we use right-hand rule number 3. You can see the person wrapping their fingers around the coil in the direction that the current's going, and their thumb points to the end that's the North Pole. And if you look at our dipole magnet, you can see that, if you look at the bar magnet, you can see that the field lines of the bar magnet, this coil doesn't show the field lines, but they come out of the North Pole, they curl around just like a dipole, just like a bar magnet, and they go back in the other end. And so notice the fingers curling in the direction of the current and the thumb pointing to the end that's the North Pole. And the North Pole is just the end of the coil where the field comes out, and the South Pole is the end where the field lines go in. And just like the bar magnet, the field lines don't end at the South Pole and begin at the North Pole. They enter at the South Pole, they go straight through, and they come out at the North Pole. And the field inside the bar magnet or inside the coil is fairly uniform and has a constant value, which we have an equation that we can use to calculate the field inside a current carrying coil. Okay, so next thing, since a wire exerts a force on a magnet, like a wire exerts a force on a compass needle, a magnet can also exert a force on a wire. So if like in the Ørsted experiment, the wire was fixed and the compass needle could turn, but supposing we take an apparatus where the magnet is fixed and the current carrying wire is allowed to move. This is just another example of Newton's third law. If the wire pushes on the magnet, then the magnet's going to push back on the wire. So here's an apparatus that we would use in lab if we were around to have lab. You see that the field goes up from the North Pole into the South Pole, so the field is going up, and the current, if we take it in the direction I showed you, is going to go through the swing perpendicular. Notice the direction of the current is perpendicular to the field, and so what we end up with is the wire swings out. So if the current is perpendicular to the field, the force will be perpendicular to that. So this is a three-dimensional phenomenon. Imagine the field, in this case, for this magnet, it's coming up, so call that the y-axis. And if the current is going through the wire along the z-axis, then the force is going to be along the x-axis, swinging out. And no surprise, if we reverse the direction of the current or reverse the direction of the magnet, the direction of the force would reverse and the swing or the wire would swing in. And so we have three perpendicular vectors, all perpendicular to each other. The direction of the current vector, the direction of the field vector, and the direction of the force. So the current goes, say, that way, and the field is up, and then we see that the force is out. So how are we going to predict this? We need a way of predicting these three forces, and so remember, so far we had right-hand rule number 2 for the straight wire, right-hand rule number 3 for the coil of wire, and now we have right-hand rule number 1 for 3 perpendicular vectors. This actually is the cross product. So the equation that we'll see in a minute for getting the force, knowing the direction of the field and the direction of the current, is a cross product equation. And if you don't remember talking about that when we talked about torque last semester, here's a chance to review it. And if you're in or have had Calc 3, then you know all about the cross product. Two vectors multiplied by each other give you a third vector in the cross product. And so if we take the standard right-hand rule, cross product rule, and we adapt it for the magnetic force due to a current carrying wire in a magnetic field, this is what it looks like. The first vector is the index finger, the current, and that crosses into the magnetic field vector, and in a mutually perpendicular direction you get the magnetic force. So this is the rule that we'll use for any situation where we're trying to find the force on a current carrying wire in a magnetic field. Right-hand rule number 2, right-hand rule number 3, and now right-hand rule number 1. So here's a situation we can practice right-hand rule number 1, and we can also see the equation for how to calculate the force. So you see the field, and by the way, the field symbol is B. Its units are Tesla. We'll learn more about that later. The direction of the current, in this case, I would call B along the negative z-axis. I would call the current along the x-axis, and the force would be along the y-axis. And so if you point your index finger along the direction of the current, and your middle finger bent at an angle, a 90-degree angle, in the direction of the field, you see your thumb points up. And so that's consistent with what we said about right-hand rule number 1. And if you look at the equation, you see the things that the force depends on. It depends on the strength of the current, the length of the wire in the field, and the strength of the magnetic field, and the angle. Here's another well, let's go back here, I guess, and just remind you that the three things that the force depends on, right? The direction of the field, the direction of the wire, the eye. I already mentioned that, but anyway. Those are just reviewing the three factors that this depends on. The I, the L, and the B. And remember, the L is not the length of the wire, it's the length of the wire that's in the magnetic field, because that's the only part of the wire that's subject to a force. And so if you take IL B sine theta, that can be written as IL cross B, because we make L the vector. So you're going to see that in the next slide. You see down near the bottom the F equals IL cross B. And also in this slide, the upper part, there's the cross product I wanted to show you. But if you glance to the upper part where it says F equals QVB, we're going to talk about this in a minute. That can be used to derive the IL cross B. So in other words, you can have, we first looked at a wire in a magnetic field, but we could also just shoot a charge, a free-moving charge, through a magnet. And remember, a static charge is not going to be affected by a magnet. But when a charge moves through a magnetic field, it's subject to a force just like the wire. The same rule, right-hand rule number 1, applies. The only thing is, when you do right-hand rule number 1, you get the force on a positive charge. If you have a negative charge, then you have to reverse the direction of what right-hand rule number 1 predicts. And so you can see the things that the force depends on. It depends on the charge, no surprise. The charge has to be moving, so it depends on the velocity of the charge. And it depends on the strength of the magnetic field, and it depends on the angle, just like the wire. So here we have a picture of a positive charge entering a magnetic field. And the final thing that I didn't talk about is, since three-dimensional, when vectors, this is a convention you need to learn, when vectors go into the page, like the magnetic field, those X's means the magnetic field is going into the page. If the magnetic field were coming out of the page, you would see dots. So the X is the tail feather of the arrow, the dot is the tip of the arrow. And so if you do your V along the x-axis and your B is along the negative z-axis, then the force is along the y-axis, and so the positive particle bends up as it enters the magnetic field, consistent with right-hand rule number 1.